morning everyone. I am Sarthak Sarkar and I will be teaching the course on integral transforms and their applications. So, starting today it will be the first lecture, and in today's lecture I am going to introduce the basic idea of integral transforms, followed by a brief definition and introduction on Fourier transforms, followed by its applications. So, without waiting much, let us start the ideas of integral transform. So, what is integral transforms? So, let me just introduce the idea of integral transforms. So, to understand the idea of integral transforms, we need to look at the differential operators first. So, what do I mean by differential operators? The differential operators, I denote it by this letter D, and D is denoted to be this following operator, which we call as the ddx. So, when we operate this operator, it is operated on a function. So, which means it is operated on a function f, which is coming from the space of C1. So, what do I mean by C1 space? The space of all differentiable functions. To all set of functions f. So, let me just distinguish between this function and this function, where f2 is also coming from the space this time of C0 functions, which means the space of all continuous functions. Now, similarly, in the same vein of differential operators, let me just introduce the idea of integral operators. So, when I say integral operators, I mean the following function I coming from the space of all continuous functions or C0 of f to the range of all continuous functions C0 f given by I of the function f equals, let us denote it by some other notation, let us say f of k as follows. So, since it is an integral operator, it is going to be an integration from some limit a to another limit b times a function of x and k, the transformed variable k and the physical variable x times f of x dx. So, the function k, we call it as the kernel of the transform. And this kernel is going to vary from each definition of the integral transforms, say starting from Fourier transform, later on to Laplace transform and many other transforms that I am going to introduce. So, it is the kernel function that changes in each of these integral operators. So, let me just introduce few more properties of integral operators. So, some of the basic properties of these integral operators. So, the most basic property is that this operator is a linear operator. So, what do I mean by the operator being linear? So, suppose if I have this operator acting on the linear combination of two functions, where your these quantities alpha and beta, these are scalars and these are my functions coming from the space of C1. So, C0 is a set of all continuous functions. So, then this is going to be defined as integral from a to b alpha of f plus beta of g times the kernel function x comma k dx. So, then of course, we can write it this function as follows. This is alpha times f of x k of x comma k dx plus beta of integral g of x k of x comma k dx. So, of course, we can see that this is alpha times I of f plus beta times I of g. So, what conclusion have we found? We have found that the integral transforms of the linear combination of the functions is the linear combination of the corresponding integral transforms. The next property is that there is an inverse of this operator. So, I denote my inverse operator as I inverse. So, I inverse of f of k is defined to be the original function if and only if I have I of f of x, the function is capital F k. So, that is the usual definition of inverse that we have. So, for each integral operator the inverse must exist. The third property that is important to these operators are its uniqueness. So, when I talk about uniqueness, I am saying that if my integral operator I of f of x is equal to I of g of x, then it implies that the functions f is identically equal to g under suitable conditions. So, we will see these suitable conditions as we move on from one case to another. So, these are some of the basic properties that these operators must have. And then of course, when we move on to specific cases, we will see more properties of these transforms from Fourier to Laplace and some of the other ones that we are going to study over our course of time. So, let me just provide you a little bit more motivation about these integral transforms. So, integral transforms have been there for the last 250 years, and the first mention of these integral transforms were of course by these famous mathematicians Laplace and Fourier. So, Laplace introduced the first mention of the transform was introduced by Laplace, that was in 1780 in his book, and the name of the book, if people want to look it up online, the name of the book is La Théorie Analytique. So, it is a book in French, La Théorie Analytique des Probabilités. So, here was the first mention of Laplace transform. Then again another famous transform that was introduced was by Fourier, who introduced his famous Fourier transform in his first paper in 1822, again by the name of La Théorie Analytique de la chaleur. So, it was a paper published in 1822. So, then of course, so these are some of the earliest mention of integral transforms. Then of course, when we start looking at these transforms, although these transforms were very easy to define, there were some obvious limitations or some deficiencies of these transforms. So, some of these deficiencies that were mentioned and also noted by many of the researchers working in this area. So, let me just highlight some of the limitations of Fourier transforms. So, also let me, for the ease of writing, let me just denote my Fourier transforms as f t. So, from now on I am going to denote my Fourier transform by this shorthand notation f t. So, some of the limitations were that they were not able to resolve discontinuous or multiscale functions. So, I am going to show you some examples as to what do I mean by these limitations in one of our later lectures. The another limitation that was noted was that these are not applicable, or I would say less applicable in non-stationary or non-linear functions, less applicable in non-linear. So, the Fourier transforms of non-linear functions are not quite well defined, as we will again see in some of our examples later on. So, non-linear I would say phenomena or functions, and we will see some examples in this case. The third limitation was that it is quite unable to resolve local, temporal or spatial scales. Temporal or spatial scales. So, what do I mean by that? So, what was shown here was that Fourier transform was able to locate the point in space where there is this sort of a spatial, it is able to resolve, it is able to tell you where there is a discontinuity, but it is not able to pinpoint with accuracy at what point in space or what point in time this accuracy occurs. And again I am going to show you with some examples as to what do I mean by this problem. So, then of course, the moment you have limitations, then people start to think about what are better ways to accurately represent our functions or phenomena with other transforms. So, then an alternative was proposed. An alternative was proposed to Fourier transform, also known as the Gabor transforms. So, just briefly I just want to mention. So, what is this Gabor transform? Well, the Gabor transform, I am going to denote Gabor transform by this curly G. So, Gabor transform of a function f is to be defined as integral from minus infinity to infinity f of tau g t minus tau e to the power omega tau d tau. So, I call this as my argument. So, this is my function of which I am finding this transform. This is the function also known as the window function, for the Gabor transform. So, let me call this as g of g, where g is my this window function. Now, it is easy to see that if I have g is identically equal to 1, my Gabor transform is identically equal to the Fourier transform of f. So, by the way, this Gabor transform was introduced by a famous mathematician in 1971 in his Nobel Prize winning work. So, of course, his name is Denis Gabor, and so this was one of the resolutions that was brought about to mitigate the limitations of Fourier transforms. So, let us now move on to more details in Fourier transform. So, specifically I am going to introduce the transform, I am going to provide the definition, and of course, more relevant issues are I am going to talk about some examples and applications of Fourier transform. So, before I move on, let me just highlight the fact that Fourier transforms are quite useful, of course, in almost every aspect of science and engineering. So, starting from linear boundary value problems, and I am going to introduce all these problems later on. So, linear boundary value problems, I am going to denote it with this shorthand notation BVP. It is quite useful to solve problems in initial value problems, or in shorthand notation I am going to call it as IVP. And as you can see that these problems arise everywhere, starting from areas in applied maths to mathematical physics to engineering sciences, you name it, and Fourier transform is already there. So, let me just start with the basic definition of Fourier transform. So, to start with the definition, I have to introduce one more notion, that is the notion of Dirichlet condition. So, what do I mean by Dirichlet condition? So, let me just again denote it by the shorthand notation DC. So, if I have a function f and f satisfies our Dirichlet condition in the interval from negative a to a, if I have the following: f has only a finite number of finite discontinuities inside this interval, right. And the second condition that it must satisfy is that f has finite number of maxima or minima, right. So, we are dealing with finite number of maxima or minima or finite number of discontinuities. Then f is said to satisfy Dirichlet condition. Now, let me just introduce, now I am going to introduce Fourier series. So, this will be introduced in our upcoming next module now. So, in this module I am going to start with the definition of Fourier series and the definition of Fourier transform. So, Fourier series. So, if I have my function f which satisfies Dirichlet condition on the interval from negative a to a, then f can be written as the following: f is a summation from n equal to minus infinity to infinity a of n e to the power I n pi x by a, right, or let me just denote it in shorthand notation. This is from n from negative infinity to infinity a n e to the power I x k n, where my values k n are these numbers n pi by a. So, of course, we can always find these coefficients a n by our orthogonality condition, where a n is given to be 1 by 2 a integral from minus a to a f of this dummy variable zeta e to the power negative I zeta k n d zeta. So, you see that this is my Fourier series of the function f, and I call these as my Fourier coefficients. So, a n's are my Fourier coefficients and f s is my Fourier series. So, 1 represents, so let me just call this series and denote it by this number 1 or I. So, I is going to denote my Fourier series. Of course, you see that Fourier series are only applicable over an interval from minus a to a. So, suppose I want to use the concept of Fourier series, we must have the fact that outside the interval my function f has to be 2a periodic. So, Fourier series are in general or necessarily must be for the case where f x, the function f is periodic. Now, in the case of non-periodic functions, for non-periodic functions, let us say f of x defined in the interval from negative infinity to infinity, that is we are going to let our a in the earlier case a going to infinity, right. Let me just also define another variable called delta k. So, delta k is the difference between k n and k n plus 1 and k n, right, and that is also equal to pi n plus 1 by a minus pi n by a, or this is pi by a. So, I have f of x. So, again from a, just go back and look at the expression for a, we are going to let a our interval going to infinity. So, f of x is given to be 1 by 2 pi summation from minus infinity to infinity delta k, well delta k, and then I am going to replace my Fourier coefficients as follows. So, this is from negative a to a f of zeta e to the power negative I zeta k n let me just, so here is the dummy variable integration with respect to d zeta, then of course e to the power I x k n, and that is the summation we have. So, notice that if I substitute the value of delta k equal to this pi by a, I am going to get the ratio 1 over 2 a as in the previous case. Now, when we take limit a going to infinity, this summation reduces to the following expression. So, let me just break down 2 pi as the follows, So, I have 1 by square root 2 pi integral from negative infinity to infinity. Notice that the summation has changed to an integral now. Again another 1 by 2 pi integral from minus infinity to infinity f of zeta e to the power negative I zeta k d zeta e to the power I k x d k. So, notice that our delta k has changed to this infinitesimal element d k, and my summation has been replaced by an integral, and I have broken down this 1 by 2 pi as follows. So, I am going to denote this thing inside this integral as my Fourier transform, or I call this as my Fourier integral formula, which is what I will be using for my Fourier transform. So, let me call this as my expression 3 for the Fourier integral formula. So, moving on, before I do some application or examples, let me just highlight where Fourier transforms are can be evaluated. So, Fourier transforms are evaluated for all those functions which are piecewise continuous, and not only piecewise continuous, but piecewise continuously differentiable, right, in every finite interval. And another requirement is that f x must be absolutely integrable. So, what do I mean by that? What I mean by that is that this integral of absolute value of f must exist and is finite over any interval, let us say from minus infinity to infinity, right. So, absolutely integrable on minus infinity to infinity. Okay. So, let me just briefly state what is the Fourier integral theorem. I have already shown you what is the Fourier integral formula. So, my Fourier integral theorem which was again published by Fourier in his 1822 paper is that if I have f of x which satisfies my Dirichlet condition and it is absolutely integrable, on minus infinity to infinity, then my Fourier integral formula which was given in my expression 3 converges, it converges to this function f of x plus f of x minus at the point of finite discontinuity at x. So, I have already given you what is the Fourier integral formula, and it tells you that if you have a function with finite set of discontinuities and it is absolutely integrable, then the integral formula converges to this average value around the point of discontinuity.